Okay, good morning. Today is Tuesday, July the 14th, and today we are going to talk about the third part of Chapter 1. And this third part of Chapter 1 is how to understand research results. All right, remember that the second part dealt with methods. How do we collect our data? Once we've got the data collected, though, what do we actually do with it? How do we make it meaningful? And most importantly, how do we share this in the pure language, mathematics? How do we share this with our fellow scientists or researchers so that they can see what we did and what our results actually are? Well, the answer in a nutshell is to do some statistics. Now, this is not a statistics course, all right? So unlike those of you in my conceptual math class, all right, we're not going to spend a whole lot of time on this, just actually this video. And oh, by the way, this is the first of just one video on all of this stuff. And so this, by the way, will be the end of our discussion of Chapter 1. And therefore, on Thursday, you will have a quiz on Chapter 1. Okay, we'll talk about that later on. Now, statistical analyses take place in a number of different ways, but generally speaking, there are two kinds of statistics. The first is what we call a descriptive statistic, and these are simply things that describe the results of a research study in a concise fashion. All right, they're just descriptive. They're not comparative. They don't help you to draw conclusions or anything else. They just describe the set of data. The other type of statistic, by the way, is an inferential statistic, which allows us to draw conclusions. We're not going to talk about those today, but we will talk about them next week, I think, soon in lab. In any event, so descriptive statistics are simply statistics that describe the results of a research study in a concise fashion. Typically, they consist of a measure of central tendency and a measure of variability. So two different kinds of descriptive statistics, all right? And we'll talk about each of them in some detail over the course of the next few minutes. Now, in addition, you can have what's called a frequency distribution, which is a depiction in either a table or a figure of the number of participants receiving each score for a variable. All right. So let's say, for example, that you had 10 data points. Let's keep it easy. We have 5. We had a 1, a 2, another 1, a 3, and another 1. Okay. My frequency distribution would simply have the score, and I'm going to list them from highest to lowest. And there are only 3 types of scores. There's 5 scores, but there's only 3 types. The frequency is simply the number of times they appear. Well, I have 1 3, I have 1 2, and I have 3 1s. Okay, and so that would be the frequency distribution. Now, pictorially, frequency distributions oftentimes will look like a graph. All right, and you can, oops. And so, you could have this kind of graph, which is a polygonal graph. You could have a bar graph. You might even have a histogram. That looks something like this. Okay. We won't get into too much detail with this kind of stuff right now. All right, but that's what a frequency distribution actually is. It's just a depiction in a table or a figure of the number of participants, all right, in frequency receiving each score for a variable. All right, so if you had 5 people do a certain task, and 3 of them scored a 1, and 1 of them scored a 2, and 1 of them scored a 3, then that represents your frequency distribution. Okay. Now, this is a video that covers some basics of statistics. Now, you cannot watch this while you're watching me, but I have uploaded the PowerPoint for this unit. And so get onto Canvas, upload that or download that PowerPoint, and then click on this link to watch. This is a Mr. Anderson video. Paul Anderson is a great YouTube guy, makes all sorts of terrific videos on a variety of different things associated with math and science. And so please take a few minutes and actually watch this video. All right. Again, you can either pause my video and open up this one, which is probably a good idea, or you can wait until the end. This video is over and then watch Mr. Anderson's video. All right. However, my recommendation would be pause my video right now, get onto this video, and then come back to me. Okay. All right, so as I told you earlier, there are two different measures of central tendency. Two different kinds of descriptive statistics. The first is a group called measures of central tendency. And what these do is they tend to describe a typical score, all right, a typical score for a distribution of scores. And in high school, or maybe even earlier than that, you learned these measures of central tendency as the mean, the median, and the mode. Now, in reality, all three of these are averages, all right? So when you describe the average of something, you could mean, no pun intended, the mean, the median, or the mode, okay? However, if you want to be very specific about what you're trying to describe, then you would use these terms specifically. The mean is defined as the numerical average of a distribution of scores. So you simply add up all the scores, divide them by the number of scores there are, and that gives you your average. The median value is the score positioned in the middle of a distribution of scores when all of the scores are arranged from lowest to highest. Okay, so you take that group of scores and you write them out again from lowest to highest, and you pick the one that's in the middle. And then finally, the mode is the one that occurs most frequently in a distribution of scores. So if you have, for example, in the previous example that I gave you, I had, I think it was 3 different ones. That would be the mode. All right, there were 5 scores and 3 of them were ones. And so 1 would be the mode. Okay? All right. Now, let's have a look at some possibilities here. All right. I'm going to give you an example where we start out, we're going to have 5 scores all together. Okay, 5 scores all together. And I'm going to ask you to calculate the mean, the median, and the mode of each of these scores. Now, the scores are going to be 80, 85, 70, 80, and 85. All right, so I have 5 kids in a class, and those 5 students take a quiz, and these are their scores. All right, 80, 85, 70, 80, and 85. All right, in no particular order here at all. Now, what I'd like you to do for these scores is to calculate the mean, the median, and the mode. All right, so we've got 80, 85, 70, 80, and 85. I don't know if that's the same order that I wrote them in last time, but it is the same set of numbers, I promise. Okay. Now, if you want to calculate the mean, then, which is symbolized as X bar, then that's going to simply be 80 plus 85 plus 70 plus 80, plus 85. Okay. Now, 80 and 80 is 160, and 70 is 230. 85 and 85 is 170. 230 and 170 is 400. So 400 divided by 5 is going to give me a mean value. My mean is going to equal 80. Ta-da! All right, this is the numerical average of these 5 scores. Now, for the median, I have to take the 5 scores and I have to write them again in order from lowest to highest. So 70, 80, 80 again, 85, and 85. Okay, so boom and boom. Now, the median is going to be the score that's simply in the middle. So I got 5 scores here. All right, the one in the middle is 80. All right, that is my median. All right, that's the score in the middle when all 5 scores are written in numerical order. Now, last but not least, the mode in this case, all right, if I look at this, and I'll do this one in blue, which score appears most frequently? All right, well, 70 only appears once, 80 appears twice, and 85 appears twice. And so this example, or in this example, I have 2 modes. All right, the modes are 80 and 85. All right, and so although this is a special case, this is what we call bimodal. All right, meaning that there are 2 modes. All right, there are 2 scores that have equally high frequencies. Okay, so this is a bimodal data set in this case. Okay, a bimodal data set. Okay, now let's move on to measures of variability. All right, there are 2 general measures of variability that we typically talk about here. All right, the first is what we call the range. Okay, and this is the difference between the highest and the lowest scores in the distribution. So I'm going to write these out again: 70, 80, 80, 85, and 85. And so I take the highest score, which is this one, and the lowest score, which is this one, and I take the difference. So 85 minus 70, and that's going to leave me with a range of 15 for this particular data set. Okay, a range of 15. Now the second thing that I've got here is what we call the standard deviation. Okay, and we'll come back to the standard deviation a little bit later, but the standard deviation is calculated as this. SD is going to equal the square, and this is an ugly formula, so don't be frightened. Oh, come on. The square root of the sum of x squareds minus the sum of x divided by n, which is the number of scores, squared, all divided by n minus 1. Okay? All right. So that is the way that we calculate the value of the standard deviation. Now, to keep our numbers a little bit simpler, let's say I have a set of scores that is just 1, 2, actually You know what? We'll do it in the correct order here. Boom and boom and boom. Come on now. There we go. And so the scores are going to be 5, 4, 3, 2, and 1. Okay, and that's it. Their frequencies are all 1, so we'll keep this relatively simple. All right, x squared is going to be 25, 16, 9, 4, and 1, right? That's that. All right, take the sum of these, okay? 25 plus 16 is 41, plus 9 is 50, 54, 55. So there it is, 55. That's x squared, okay? The sum of x is simply 5 plus 4 is 9, plus 3 is 12, plus 2 plus 1 is 15, okay? And n is 5. There's 5 different scores here. So in this particular example, this is going to equal the square root of 55 minus 15 over 5 quantity squared divided by 5 minus 1. Okay? So 15 over 5 is 3. 3 squared is 9. 55 minus 9 is 49. 5 minus 1 is 4. 49 over 4 is a little over 12. So 49 divided by 4 is 12.25. And if I take the square root of that, and again, I'm cheating, I'm using my magic number box, the square root of 49.25, I'm sorry, 12.25 is 3.5. All right, so the standard deviation is 3.5. Ta-da! All right, and so that's how you would calculate that. Now, it's an ugly number and an ugly formula, and I won't ask you to calculate this on a quiz or a test, but for your research projects, you are going to have to learn how to do standard deviations on, for your research papers. All right, so that's the way that it goes. Now, let's look at why we actually do this. All right, let's say we had a data set that was 70, 80, and I'll write these in order: 80, 85, and 85. Okay, and I have another data set that's 20, 40, 80, 120, and 140. Now, if you calculate the average of this, which we've already done, all right, it turns out that the average is 80. Okay, if I calculate the average here, guess what? The average is 80. What? How can that possibly be? All right, so what if you only looked at the measure of central tendency, you would say, oh, well, these two groups of scores are exactly the same. They both have exactly the same average. But obviously, there's a big difference here. The range for this one is 15, whereas the range over here is 120. All right, and so even though both sets of data have the same average, the bottom set here is much farther spread apart. All right, the data points are all over the place, and so there's a much greater standard deviation, much greater range. All right, and so we need to use both central tendency and variability when we describe a data set. All right, so those are the two kinds of descriptive statistics. Okay. Now, a frequency distribution. All right, I already showed you one of these, but a frequency distribution simply organizes the data in a score distribution so that we know the frequency of each score. It tells us how often each score occurred, and it typically takes on a bell-shaped curve with lots of individual points in the center and fewer points toward the ends. All right, and so the frequency distribution let's say for this one, we had 85, 80, and 70. There are only 3 unique scores here, but 85 appeared twice, 80 appeared twice, and 70 appeared once. And so the 85 has a frequency of 2, 80 has a frequency of 2, and 70 has a frequency of 1. So this is the frequency distribution. All right. Now, the most frequency distributions from regular data sets are what we call normal looking. All right, they are shaped like a bell curve. All right, and I know that you've seen a bell curve in math. All right, it's simply the graph is simply shaped like this. Okay, so the normal distribution is a frequency distribution that is shaped like a bell. All right. And the key for a normal distribution is that the mean and the median and the mode are all the same. This is key. Very important. Make sure you remember this. All right, the mean, median, and mode are exactly the same. Now, the way that a normal distribution works, because of the bell-shaped curve, we know for a fact that if the mean, median, and mode are all equal, then 68% of the scores are going to fall within 1 standard deviation of the mean. Okay, so if this line here is the mean, then we've got, if we go 1 standard deviation this way, S, D, and 1 standard deviation this way, all right, 68% of the scores, 68% of the scores are going to fall in that large portion. 95% will fall between here and here. All right, within 2 standard deviations of the mean. Again, this represents 1 SD, and this represents 1 SD. And then finally, 99% of the data points will fall within 3 standard deviations of the mean. Okay, we'll play with this. For those of you in conceptual math, we'll play with this some more later. But for now, just keep that in mind. Now, this is the normal curve showing the standard deviations. Now, this one actually divides them by half of a standard deviation. All right, so this is the standard deviation given on the bottom. So half a standard deviation, this is 1. So between here and here, all right, this represents about 68% of the scores. All right, 68%, which means that between here and here is 34%. All right, fall within 1 standard deviation below the mean, and this is another 34% on the other side. Okay, between here and here, this represents 95%. Okay, all the way across, meaning that this is what's half of 95. 45 was 2.5, so 47, about almost 48% here, between here and here, and here and here. All right, and then between this point all the way across, to here, all right, this is 99% of the data points fall between these 2 points on that standard curve. Okay, and so if we know that our data is normally distributed, there are a lot of statistical analyses that we can use using standard deviations and this bell curve in order to predict where the next set of data points might fall. Okay, now bell curves are often drawn to look like the one on the screen now, but all 4 of the curves on this slide are also normal distributions. Obviously, they're all different. So what's the difference between the blue curve, the red curve, and the yellow curve. If you look at all three of these curves, you'll notice all three of them have exactly the same average, right? The mean value right in the middle, 50% of the scores fall to the left of this value, 50% of the scores fall to the right of this value. So all three of those curves have the same mean, all right? So they have the same measure of central tendency. What's the difference here? Well, the difference comes in their variability. The data in the blue data set is not very variable at all. Most of the data is very close to the mean. In the red data set, the data is more spread out, and in the yellow data set, the data is even more spread out. Okay, even though all three data sets have the same mean value, the data is obviously distributed differently, although all three of them are normally distributed because the mean and the mode and the median are all the same. Now, the green line or the green curve here is a little bit different, all right? It's still a normal distribution, but the mean of this one is different than the mean of the blue, red, and yellow lines. All right, in this case, it's located obviously to the left, and so the mean value for the green data set is less than the mean value for the blue, red, and yellow data sets. Okay, but those are some differences that you can use to describe the normal distributions. Okay, now this, my friends, is another little Mr. Anderson video on standard deviation. And so either pause this video now and go upload this into your browser, or you can open up the PowerPoint that I put on Canvas and use that and just click on the link. It's a hyperlink, so it'll take you right to the video. All right. I do suggest that you watch it first and then come back to me. But if you want to wait and come back, that's fine. That's fine too. Now, let's do another calculation of standard deviation just so that we are all on the same page. So let's say we have a data set that consists of 0, 2, 4, 5, and 7. All right. So again, there's 5 scores here. All right, my values for scores 7, 5, 4, 2, and 0. The frequency is 1 for all of them, so I'm not going to change. I'm not going to change that. My value of x squared. 7 squared is 49. 5 squared is, come on now, 25. 4 squared is 16. 2 squared is 4. 0 squared is 0. Okay. Now, the number of scores here is 5. All right, so that's n equals 5. The sum of x squared is 49. Come on now, please. 49 and 25 is 74. Plus 16 is 90. 94. And there we go. Okay. Now, if I go back to my formula for standard deviation, remember it's the square root of the sum of x squared minus the sum of x divided by n squared divided by n minus 1. Now, I did make a mistake with this we're just, I don't know, I can't remember if I did this right in the last calculation now, but you can go back and check this. So the sum of x squared is 94. The sum of x is 7 plus 5. 7 plus 5 is 12, plus 4 is 16, plus 2 is 18. And so 18 squared over n is 5, all divided by 4. Now, 18 squared is equal to 324. Divided by 5 is 64.8. 94 minus 64 point, well, actually, nope, that's not right. 18 squared equals, divided by 324 divided by 5 is 64.8. 94 minus that is going to be 29.2. 29.2 divided by 4 is 7.3. And the square root of 7.3, dun dun dun, is going to be 2 point something or other. So 2.7. All right. So the standard deviation of this data set is 2.70. All right. 2.70. Now, what's the mean? Just for kicks and giggles. 0 plus 2 is 2, plus 4 is 6, 11, 18. 18 divided by 5. Oops, that's 78 divided by 5. 18 divided by 5 is 3.6. All right. So the mean is 3.6. The standard deviation is 2.70. Okay. All right. Now, percentile rank. When you describe the percentage of scores below a specific score in a distribution of scores, okay? So, for example, if you have a bell curve that looks like this, all right, if you want to describe the 85th percentile, well, that's going to be, actually, let's use the example here. If a score is 1 standard deviation above the mean, okay, so this is the mean value right here, all right, 1 standard deviation, we'll move here, okay, above the mean is this, all right, so 1 standard deviation. Now remember, that should be 34 percentage points. All right. So if a score is 1 standard deviation above the mean, it has a percentile of 84%, right? Because right here is 50% plus 1 standard deviation is 34. So 50 plus 34 is 84. All right. And so this is the 84th percentile. The mean is 50%. The standard deviation is 34%. If I went 1 standard deviation below the mean, okay, then this point right here, if this is, again, 1 standard deviation here, then it'd be 50 minus 34, all right, which is, this would be the 16th percentile. Now, what does that mean? Now, what that means is that if all the data in here, the green represents 84% of the data. All right. In other words, 84% of the data fits under the bell curve in the area that I've shaded green. Okay. If I, let's choose a different color here. I don't know what cyan is. But if I just looked at this, I'm not coloring in the lines. Sorry. But this would be 16% of the data. All right. if I did, we'll do yellow. All right, if I colored this, all right, this area, yellow represents, you can barely see this, sorry, that was a bad choice, but that's 50% of the data, all right, the yellow, all right, and that's where the percentile rank area or idea comes from. Finally, let's talk about a skewed distribution. Although most natural data sets are normal, all right, in other words, they have that pretty little bell shape, and you can see them in the data itself, sometimes distributions of data are skewed. A right-skewed distribution is an asymmetric frequency distribution, meaning it's not a pretty bell, in which there are some unusually high scores that distort the mean to be greater than the median. A left-skewed distribution is an asymmetric frequency distribution in which there are some unusually low scores that distort the mean to be less than the median. All right? Now, that's all fine and good. I'll let you write down the words here. All right? But if it's skewed to the right, you've got a couple of unusually high scores. If it's skewed to the left, you've got a couple of unusually low scores. Now, a picture is worth 1,000 words, and so here we are. Let's start with the graph in the middle. All right, that is the normal distribution. In this case, the mean, the median, and the mode are all the same. Okay, and that's what makes it a normal distribution. All right, it's a perfectly symmetrical and balanced distribution. Now, if, on the other hand, you have a negatively skewed distribution, that means that your mean, I'm still in yellow, but that the mean is less than the mode, okay, or the median for that matter. On the other hand, if the mean is here, all right, what that means is that the mean is greater than the mode, okay? And so this is a positively skewed distribution. Now, right skewed is when the mean is greater than the median. Left skewed is when the mean is less than the median. So if the mean is negatively skewed is also known as left skewed. Positively skewed is also known as right skewed, okay? Because the mean is further to the right than you would expect it to be. Here, the mean is further to the left than you would expect it to be. And those are examples of skewed distributions. All right, so that is the end of this, this video. I hope that you're not too confused, but I will be available to answer any questions that you have afterwards. All right, boys and girls, have yourselves a lovely day, and I hope you learned something.